Hello, everybody. Thanks for coming. So, first of all, let's do some introductions. Two of us going to be speaking today. My name is Julian Hyde. I work for Hortonworks. I'm involved in various Apache projects, but this one is mainly about Apache Calcite, which is the query planning framework that's underneath Apache Hive, Apache Drill, and several other projects. And next to me is Tomer Shiran, who's CEO of Dremio. He's going to be speaking towards the end of the presentation about our integration with Arrow. Tomer is also a PMC member of Apache Drill. Originally, I was scheduled to do this with Jacques Nadeau, who's author of Apache Drill, but he couldn't make it. Okay, so polyalgebra. You probably haven't heard of polyalgebra before because we made up the word to describe this new concept. And this presentation is kind of about a mixture of existing technology, tools, techniques, and kind of a general direction that a few of us see the world going in. Arrow is part of that kind of movement. Calcite is part of that movement. So kind of a general trend we see, kind of away from traditional databases towards new ways of dealing with data. So polyalgebra is kind of an extension to the relational algebra to deal with non-relational data. So data which is dynamically typed, which has complex records, in other words, records that look more like JSON documents, streaming data, machine learning, but still kind of draws on the benefits of a traditional query planning, query optimization process, which are the benefits of that are well known. So we're going to be touching on a big ecosystem of many of these are Apache projects, but you've got commercial projects in there like Splunk, because this is all about hybrid systems, systems that are interchanging data at runtime, the ability to do federated queries and so forth. But some of the things in the ecosystem are data stores. Primarily, they're where the data lives. They have a query language, but they're not able to run, let's say, machine learning algorithms, arbitrary code, and so forth. Other things in this system I'd categorize as engines, that they can store data, but primarily they connect to data that's stored somewhere else. And they're often very parallelized distributed systems, high performance, specializing in perhaps particular kinds of queries. And then what we're actually going to focus on in this talk, this kind of vision is not exclusive to these technologies, but we're going to focus on Calcite, Drill, and Arrow. Calcite does the query planning, has the relational algebra in it. Drill is an example of an engine, but it's an engine that Tomer and I have both worked on. And then Arrow is an up-and-coming technology to allow efficient in-memory representation of data and interchange between data engines. So the old world relational database, it's actually where I come from. I started my career at Oracle. You use SQL to run the queries. You define your schema before you start loading it. Has good solid metadata security and so forth, and it has this principle of it has a query planner. It has this principle of data independence, which basically means you can add indexes to your tables and things run faster. And that's one of the kind of core principles of databases. Then Hadoop came along and kind of blew all that apart. Kind of got rid of metadata, got rid of the SQL language at first. And then had a much wide variety of workloads and much wide variety of databases, graph engines, that kind of stuff. And what I claim is that the values from the DBMS world, relational algebra planning, are still applicable to the new world of data. The trick is to kind of carry them into the new world without the restrictions of the old DBMS. So the problem space that we see is that we want to have all of these different languages, not just SQL, but languages like Spark for machine learning, HBase, graph languages. We want these all to be running, and our data might live in a variety of data stores. So it's kind of the problem that people writing compilers have as well. They want to support many front ends and many back ends, and they don't want to write n-squared compilers. Ideally, they'd like to write one compiler that does the optimization, and then so you write n front ends and n back ends, and then you only need to write one compiler. So the approach of using relational algebra is trying to achieve that. So relational algebra, it's a mathematical theory, basically. It was invented by a mathematician, Ted Codd. I misspelt his name, or PowerPoint corrected his name to something incorrect. Ted Codd, who was working for IBM, kind of invented relational algebra to solve the problem that he saw of databases which were very, very fragile and brittle. So this is the underpinning of the relational database. It's an extension to mathematical set theory and has a small number of kind of well-defined mathematical operators, select, filter, join, sort, and so forth. The reason it's useful is that it allows query optimization. Because it's a mathematical theory, it's well behaved, you can have theorems in it, and those theorems can be used to transform relational expressions to produce something that is semantically the same. In other words, it'll produce the same results for any given data set, but is more efficient. That's the kind of the basis of all query optimizers. And I think the word relational is kind of a disparaging term these days. It's only relational, it's only flat records. And I'm trying to explain that the benefits of relational algebra still work on data which is not relational. So here's an example of relational algebra to kind of make it a bit more concrete. SQL query on the left-hand side. This is parsed, validated, and converted to the relational algebra operators on the right-hand side. So it starts off with a couple of table scan operators. A join has two inputs and one output. A filter implements a where clause. Aggregate implements the group by clause. A filter after that basically implements the having clause. A project, we project out two columns. And then lastly, we sort by the count. So, and any SQL query you can name can be converted into relational algebra with basically that same set of operators. So that expression is what the query optimizer works on. And then it produces physical operators, so it might, we might decide to use a hash join to implement that join, and that's what actually gets executed. And it really doesn't matter which engine you're using, whether you're using Hive or Drill or Oracle or MySQL. What's going on inside is pretty similar. And by the way, what's going on inside non-relational databases like MongoDB is pretty similar as well. So yeah, some more operators. So union. The set operators are kind of built-ins in this set. And then subquery, there isn't actually a subquery operator in a relational algebra. So you see that you've got a union, which represents a subquery, and then immediately on top of it is the filter. So a subquery really is just a namespace. It's a kind of a scope for the SQL language. But it's, when it's converted to relational algebra, the subquery kind of disappears. Lastly, the relational algebra does support DML. So, we have an insert operator that produces, well, depending on how you want to do it, it either produces no result or it produces a result which is like a row count, a single value that just says, I inserted 100 rows. And then values is like the constant value in relational algebra. So values, this is a constant table, if you will, with two columns and two rows. It's kind of pointless, but any programming language has constants in it, so it makes sense for relational algebra to have constant values in it as well. Okay, so this is a kind of quick example of how query optimizers work, and the basic principle is by applying these relational transformation rules. So here we've got I've kind of turned it on its side. The data's flowing from left to right here, from table scans through join, filter. And what you'll notice is the filter, the action equals purchase, the purchase column only exists inside. Oh, and by the way, this is a kind of a federated query. So it's reading, one data set is from Splunk. Splunk really kind of only has one table, which, it has all the data in it. And MySQL, which is just a JDBC data source. So the action column comes from Splunk. So it's kind of not efficient to join the data and then apply the filter. It's more efficient to push the filter down into Splunk. So we do that by applying a couple of transformation rules. And so what happens is the filter and the join swap places. So this is semantically equivalent because the rules are valid theorems, and it's more efficient. It's more efficient for two reasons. First of all, we filter the data before it gets into the join, so the join is just doing less work. And secondly, the data never even leaves Splunk. It never gets converted into Splunk's wire format. So it's again less work for the Splunk system to do. So the way the optimizer works is it applies a lot of these transformation rules, and then after it's applied a lot of transformation rules, it uses a cost function to figure out which is the cheapest thing that it's produced. So it's producing a whole collection of equivalent statements of the same query, and then it chooses the one with the lowest cost. And this probably has there's probably some more optimization that can be done here. Like for example, Splunk has the ability to do lookups, so we could actually push the join into Splunk, so Splunk could read directly from MySQL rather than us pulling the data out of Splunk. But anyway, that just illustrates a single set in the optimization process. I'm going to do a quick demo here of Calcite. So Calcite is primarily it's a library that you embed in other things, but it has a SQL parser and validator, and it has some basic implementations of the relational algebra, so you can run it in a kind of an embedded database in a JVM. So, and I'm using SQLine, which is just a generic shell that you can use to connect to any JDBC data source. So I'm going to connect to Calcite with no arguments at all, and what you end up with is an empty database. It has two tables, the two system tables, called tables and columns, and that's all that's there. I can say select star metadata.tables, and I just get the same result. So this thing can run queries, but it only has two tables available to it. I'm going to connect now using using a model file, which is let me just show you this model file. So the model file is a piece of JSON that basically says I'm going to have one schema. The schema is called sales. I'm going to use a particular schema factory called CSV schema factory. And so what this means is when I connect, there are the two tables in metadata, but there's a new schema called sales. And in fact, this so it's based on this directory here, which has two files in it. deps.csv and emps.csv.gz. So this adapter is basically able to find any CSV files, and each CSV file, it basically makes it appear as a table. So I can say select star from sales.emps, and there it is. And I can then ask for the plan. So what this is going to do is basically convert my SQL to the relational algebra, and it's the relational algebra that it's actually going to execute. So this is a very simple one. It's a CSV table scan. So it's the scan relational operator applied to a CSV file. And if I say, I don't know where, let's see, age greater than 10, it's a CSV table scan with a calc on top, which is an implementation of the filter. So this adapter isn't particularly smart, but what I can do is if I just ask for one column, if I just say select age from sales.emps, it actually it just uses a table scan. So it's taken that project and pushed it down into the table scan, so it's actually just asking for fewer fields from the CSV. A more sophisticated adapter like a MongoDB adapter, a Splunk adapter or so forth may be able to push projects and filters and aggregations and all that kind of stuff down into the underlying data source. And that's what Calcite does particularly well. Okay. So Calcite is a framework. It has a collection of APIs. It has kind of at the core of it is a representation of the relational algebra. So table scan, filter, project, union, and so forth. It has a SQL parser, and it has an SPI to do the metadata. So you implement the schema SPI, and then Calcite will call you, and you get the chance to tell Calcite what tables exist. So if you want to add a new data source, the first thing you do is implement that schema SPI, which, CSV schema factory, it is an example of that schema SPI. And then transformation rules. A transformation rule matches one or more relational operators and produces a tree of relational operators. There's a lot of built-in ones, there's over 100 built-in ones, but you can write your own that match your particular, either the built-in relational algebra or perhaps your extensions to the relational algebra. And then there's a whole variety of things for cost and statistics, so estimating the number of rows that are going to come out of a join, asking a relational operator which of its output columns are unique, that kind of stuff. And then it comes with a driver stack, distributed JDBC driver, and so forth. So the planning process is, what goes into the planning process is a SQL parse tree, which is then converted to relational algebra. And then it kind of goes through this dynamic programming process where it looks at the relational algebra, figures out which rules can match, and then of the 25 rules which are able to match, it puts them into a queue and figures out which ones are likely to do the most benefit, because it's trying to find the best. It's trying to find the best result as fast as it can. And then it basically fires one of these rules. The rule produces, the rule may not produce output, but it often does produce output. And so that's now a new expression. That expression now goes into the space of relational expressions, and then that new expression may actually allow some new rules to fire. So those new rules get put into the queue, and it basically keeps on firing the rules, generating output, and queuing up new rules until it's found something that's cheap enough, or it's run out of things to run out of rules to fire. Any questions at this point? No. All right. Well, feel free to stop me and ask questions if it isn't all making sense. So SQL is only one of the ways you can actually build relational algebra. We have an algebra builder API that kind of, for those of you familiar with Spark and Flink and cascading. It's kind of a it's basically a builder that allows you to build relational operators, and what comes out at the end of it is it doesn't execute a query. By the time it reaches the print line, it's basically created a relational expression. So when I call print line at the end of this, as you can see, I start off with a scan. I then put an aggregate on top of it, and I do a filter. So the bottom is Calcite's representation of a plan, and it's indented so that your table scan is the kind of leaf node. It flows into the aggregate and then flows into the filter. Kind of the value out of the builder is I can reference columns by name, like C, and I can use easily use you define a sum aggregate and a count aggregate. But I could create these relational operators by hand if I wanted to. And in fact, if I was to add a new relational operator that the builder doesn't support, then I could very easily mix it in with what the builder's produced. Then this is going to be the input to the relational planning process. And by the way, this on the left-hand side is equivalent to this SQL statement. But if you wanted to implement your own language, then the builder API is kind of where you'd start. You'd write your parser for your own language, and then start building relational operators or your own extended relational operators, and produce a plan, and then enter the planning process. So kind of let's look at some ways that non-relational, post-relational systems kind of differ from this. One of which is kind of the shape of the data. Rather than being flat records, they might be documents, key value stores, graphs, and so forth. Then there's the operators themselves. They might be non-relational operators. The OLAP world has non-relational operators like pivot and hierarchize. There are operators that are written by you yourself. There are operators that are written in kind of Python libraries and things like that. And then another factor is whether there's any schema, because traditional SQL relies on having a schema before you execute the query. So we're going to go through some of those examples and see how they kind of map into what Calcite does. So complex data, and this is an area that Drill is particularly strong in. Drill is a SQL database, but it also handles JSON data very nicely. It turns out that you only actually need 2 new relational operators in order to deal with complex data. One is an unnest operator that kind of takes a nested collection and flattens it out. And then the other is collect, which takes a flat relation and is able to kind of build it into a kind of cluster it together into a document. And collect is actually an aggregate function. So you would do group by what you want to be the key of the document. So in this case, you got employees, and nested inside employee is a number of pets. So if you have a flat normalized relation of employees and their pets, you would say group by employee name and employee age, and then the pet data would kind of go into this nested collection. And the collect function builds a nested collection. Let's look at a nest. Drill actually has syntactic sugar for a nest, which is called flatten. So flatten is a function you can put in your select list. It basically, every time it sees a list, flatten will, as you can see, Bob's got two pets. So when flatten calls this, it produces 2 rows with Bob, and each of those sub-records has basically created a new flattened record. And then because Ken doesn't have any pets at all, Ken just disappears. So it's kind of like a join to a table nested within the data. And in fact, in the SQL standard, the unnest operator, it is exactly that. So we're saying from employees, comma, unnest. We're joining the table to the collection inside itself. So, internally we represent that as the unnest operator, but if you're using drill, you can also use it via flatten. So let's look at how we can apply query optimizations to unnest or flatten. So one of the common things we want to optimize is pushing filters through it. And it turns out if you've got a filter that's applied not to the, if you've got a flattened data set and you've got a filter expression that applies to kind of one of the outer columns, in this case it's the age column, then you can very easily just push the filter through. So we apply this filter and nest transpose rule. It's not actually in Calcite. Kind of, I just dreamt it up, but it's, you know, it's kind of easy to dream up rules, and you know, as long as they're kind of mathematically valid and so forth. So the query at the top is equivalent to reading from employees, only taking the ones whose age is less than 30, and then only then, you know, only bothering to do unflatten on the employees whose age is less than 30. Another optimization we can do is pushing down project. Again, a very common optimization on pretty much any data source. If we're only interested in the name of the employee and the name of their pets, we can push that project down to the table scan to say only read those columns off of disk. And if you're using column-oriented storage like drill reading from Parquet, this is going to involve a lot less I/O than reading all of the data. So once you've written each of those rules, you can add those 2 new rules to the 100 rules already in Calcite. And now Calcite is doing a pretty good job optimizing queries on document-oriented data. You haven't needed to write a whole database from scratch. This is the point. You've added 2 new rules. You've added 2% new DNA to you know, the existing database DNA. So late schema. In the old days, and you know, this applies to Oracle, but also to conventional DBMSs like MySQL and Postgres. You do create table. You have to do create table before you start putting data into it. So that you know, you're defining the schema in that way. In Hive, you can define schema a bit later. You can put your files in HDFS, and only then actually say what the data type is. But you still have to define the data before you do the query. And in drill, you don't actually have to. You need to tell it the table exists, but you don't need to tell it what columns there are. And if the table is, for example, a JSON document, it figures out what the columns are as it's running the query. And this kind of manifests itself in how drill does select star. If you say select star from employees, you get 4 columns back. But if you're only interested in employees under the age of 30, you get Ken, and Ken doesn't have a star sign. So as far as it's concerned, there is no star sign column. So you just get fewer columns back. So in a sense, this kind of the schema, in other words, the set of columns that the data has, is kind of a property of the data, not a property of the table definition. This is a useful thing because people want to kind of get going on their data, and you know, drill allows that kind of use case. You know, we can extend this model to deal with it. So one of the things we do under the covers is it actually helps to have strong typing in the system underneath. And this is a lot like implementing a JavaScript engine. That, you know, JavaScript engines, as far as I know, are kind of strongly typed underneath. They just give you the illusion of being weakly typed on the top. So internally, we translate this to map functions. So each row is represented as a collection. And when I say e.name, it's actually internally translating that to, you know, look up the name property in this map. You know, that satisfies Calcite's type checker, and the query gets through query optimization. And also, you know, another part of this late schema is we don't know what is the data type of the age column. But the fact that we're saying age less than 30 means we probably want an integer. So it does an implicit cast to integer. There's various ways of doing user-defined operators. And Calcite has a couple of ways. In addition to building your own relational operators, you can define table functions and table macros. A table function is a Java function that reads a relation and produces a relation. And then my sample is something where it's reading, it's going to return 15% of, you give it 100 rows, it'll return 15 rows out. It'll give you 15% of the input rows. My filter is an example of a table macro. And a table macro doesn't deal with data at all. A table macro is a function that takes a parse tree, a relational algebra tree, and returns a relational algebra tree. So those of you familiar with list macros, it's the same kind of idea. A table macro actually alters the expression that the system is seeing. So at runtime, if you look at the runtime plan, my filter will not appear anywhere in it. My filter will generate a filter on top of a table scan, and it's completely expanded at even before planning time. And views are basically a form of table macro. A view is a table macro that just produces a parse tree, a relational algebra tree. So using table macros, you can do things like parameterized views and so forth. Very, very powerful feature. I've got a few slides about views and materialized views. I'm going to skip through them fairly quickly. But the basic idea is kind of illustrating that views and materialized views are ways of kind of manipulating relational algebra. A view is a way of storing a piece of relational algebra on disk that you can use as a kind of shorthand for queries. So whenever you reference this view called managers, it kind of expands that tree. Whenever I say managers, it expands the piece of relational algebra here into the query that you wrote. And then it goes and optimizes it. So as it optimizes it, it's pushing down filters, and so it ends up as more efficient. It doesn't literally evaluate the entire view, as part of the query. Materialized views are kind of views backwards. So materialized view is, here's a table whose contents are the same as this query, and then when you execute a query that could use it, in this case we have a summary table that groups by department and gender, and has the number of employees in the department. When I have a query that's asking for the number of employees in department 10 who are male, it's basically able to rewrite that query to use the summary table. So it's kind of doing view expansion backwards. All right. And then the last area, this is just a couple of slides. I spoke in this a lot more depth yesterday. Streaming queries they're kind of relational, but they're tables that you're writing queries on, not tables that exist, but streams of data which flow continuously. The queries run continuously. In fact, they never end. But it turns out that a lot of relational algebra can be run on streams, and it's a very useful high-level language to build streaming analytics, or indeed analytics that basically combines data from the past, i.e. tables, and data from the future, which is the stream. So, and because you're combining it within one language, the system can deal with the difficult process of maintaining kind of summaries, rolling windows, comparing the average price today with the average price over the last 3 years, which involves probably reading a data structure from memory and another data structure from disk. So it's a very powerful construct. Again, just an extension to the traditional role of the database. And then, hybrid systems are another goal of this. Your data stored in various places, various formats. And the other piece of this is when we've optimized and produced a plan for a hybrid query, we actually need to be able to have a hybrid runtime. So data is stored in this system, it's being processed by this engine, and that engine needs to talk to another engine. So in order to do that, a few of us realized that we needed a common data interchange format. And that data interchange format is Arrow. It's a new project, and Tom is going to speak about that.
Cool, thanks. So I'll just spend a few minutes talking about Apache Arrow, which is a new project that we, as a community, announced about a month ago. And this is a combination of different companies as well as open source projects that have basically come together to create a columnar in-memory format. And so at a high level, this was announced February 17th, and the focus here is on columnar in-memory analytics. So, I think early on especially in the kind of the big data landscape, it was all about just data on disk, right? We had a bunch of data formats, Avro, or initially CSVs, Avro, and so forth, kind of row-oriented. Then we started talking about, okay, how fast could things be if they were in memory? And I think this is kind of that third generation here, which is about keeping the data columnar in memory, right? So just like we have things like Parquet and ORC to store data in a columnar format on disk, which makes things a lot faster. So you think about the use cases where you have 200 columns and you only really need 2 of them for your query. Makes a lot of a huge performance difference, but keeping the data columnar in memory provides yet another level of performance enhancement that can be significant. So in many workloads, we expect to see anywhere from 10 to 100x performance improvement by storing the data in a columnar format in memory, which lets the kind of modern CPUs take advantage of their parallelism. The other nice thing here is that we, as a community, we're building this together with a bunch of the open source technologies that are out there. So Arrow is a joint initiative between Apache Drill, Calcite, HBase, Impala, Kudu, the Python community. So Pandas is integrating with Arrow as kind of the standard way to store data in memory. The R community has now embraced Arrow as well as their in-memory format. Spark is adding Arrow, and we'll have that by the end of the year. So this is really how all data will soon be represented when you talk about kind of the big data stack. It's also designed to work with different programming language. So up until now, we've had different systems kind of say, okay, you can use Python to do some things, you can use other things, but the reality was that it was just too slow, right? So it was nice from a marketing standpoint to say I can write my program in Python or write pieces of it in Python, but the reality is we want it to be as fast as if I was writing the whole thing in a JVM language. So what Arrow allows us to do is by having native support in Java, C, C++, Python, Ruby, and so forth, every language becomes a first-class language. So we can have Python UDFs in our SQL queries, and that will perform just as fast. Right? So those are the kind of things that this enables. And then Arrow also, when we talk about columnar, it's actually shredded columnar, which means that if we have a lot of data now is nested and has arrays and things like that, being able to represent those types of complex records in a fully columnar format is a much harder problem that Arrow is also addressing. And so, like I said, most of the technologies that you are probably using from a big data context are on board with this project, and there are committers from all these different projects. So the focus here is on the first thing this provides is a huge performance boost, right? And it does that by taking advantage of the characteristics of modern Intel CPUs. And so there's something called vectorized operations or superscalar operations in today's Intel CPUs. And what that allows them to do is run the same operation on multiple values. So take an array of integers, for example, and you want to, say, add 3 to each of those values. The CPU can do that in a single cycle by using these SIMD operations. So it loads that kind of byte array into memory, and then in one cycle does the operation in parallel on all of them. So if we can organize the data in a columnar format, the way you see here on the right-hand side of this slide, where we have all the session IDs first, then we have all the timestamps, and then the source IPs contiguous in memory, then the CPU can actually do those types of things, as opposed to the way it was traditionally done, and the way it's done today in most of these technologies is that it's row-oriented in memory, which means that the CPU can't do those types of things. the side effect here of, okay, so the way this started is that, drill had this kind of in-memory columnar representation that was making execution really fast. And then other execution engines and storage systems in the big data ecosystem wanted to add those types of capabilities as well. And so the nice thing is we're all operating under kind of the Apache software foundation and in an open source, so we can actually share the work and share the technology. And as a side effect of that, of all of us using a single standard for this, we can actually share memory between systems. And so what you realize is that today we're spending 70 to 80% of the time when you're querying, one execution engine is reading data from one storage system, it's 70 to 80% of the time could be spent just serializing and deserializing data. And then that, of course, is done differently for any two combination of any two pairs of systems. So with Arrow, there's one standard memory format. It's used across the entire ecosystem, and you can share data between different programming languages, between different systems. So it makes everything much more efficient, and you get to the reality of actually supporting multiple systems. So hopefully that gives you guys a good overview of what we're up to, both from a query planning, optimization, as well as kind of execution, to really enable these kind of multi-source and multi-execution engine environments that we're operating under now, instead of the monolithic kind of relational database model. So with that, if there's any questions, maybe one or two, because I think we're close to out of time. Yeah, so the question was, does Arrow rely on shared memory? So Arrow actually have both an IPC and an RPC library. So the IPC is based on shared memory. So that allows things within the same server or the same node to actually share memory, and that uses, or to share Arrow buffers, and that uses shared memory. And then there's also an RPC library that allows communication with Arrow across the wire.
For complex data type, the unnest kind of brings the data back to the relational world. Can I do, or does Poly-algebra support pushing something within, like for example, pushing a filter in the nested data?
Yeah, you can work on the data in a nested format. So Arrow can represent document-oriented data, and Poly-algebra can, you can do query optimization on.
This should be outside of the relational algebra world, right?
No, well, it's extended relational algebra, so it's algebra that can work on data, and the data does not have to be relational in order for the algebra to work on it. All right, I think that's all questions. If there's any more, then Terma and I will be at the front. Thank you all for coming.